Hey everyone. So what I want to do in this video is a quick overview of how to make scatter plots in Excel, Google Sheets, and LoggerPro. So I'm going to do a brief overview of what scatter plots are, why they're useful, and some general pointers, and then look specifically at how to do those graphs in Excel, Google Sheets, and LoggerPro. And I'll leave timestamps in the description so you can quickly find which program you're looking for and look at the instructions specifically for those ones. So scatter plots are used a lot in analyzing different kinds of scientific data. Let's say I have an experiment where I've got two measured quantities and I'm trying to find a pattern between those two measured quantities. It could be something on projectile motion. So I'm dropping an object from different heights and I'm measuring how long that thing takes to fall. So those could be my two variables. Or maybe I'm applying a force to some object and I'm measuring the resulting acceleration of that object. That could be my two variables. Or let's say I'm giving someone a certain dose of some kind of medication and I'm measuring how long does it take that person to get better with that particular dose. These would all be examples of finding a pattern between two kinds of experimental measurements. And again, these scatter plots can do a lot of different things. First, if there's a pattern in that data, it helps make that pattern visual rather than just looking at a stream of numbers, which it can be hard to interpret what that data actually implies or what that data means. It makes those patterns visual. It allows us to match this data with specific kinds of mathematical patterns and generate best fit equations so we can quantify these patterns. It also helps us identify what levels of noise are present in our data. All data has noise, and we probably want to know how much. These graphs can help us do all of this and more. So, very quickly, what is a scatter plot? Okay. For a scatter plot, I've got, again, two variables, and I want to find a pattern between those two variables. So, I'm going to make a graph where one of those variables is going to be graphed on the horizontal axis. We'll call that one variable x. And the second variable is graphed on the y-axis. So we'll call that variable y. And again, this data, if I try to just look at this data as a stream of individual data points and trying to find, well, what pattern is there in this data, unless it's some very simple data, is going to be really, really hard to do. So if we look at this and try to find a pattern between my variables x and y, this is going to be really hard to identify. However, if I make one of these scatter plots and put dots for each combination of x and y, I'm going to put a dot on this graph corresponding to what's the value of x, put that on the horizontal axis, and what's the value of y? Put that on the vertical axis. And in this particular case, when I graph this data, we see this kind of wavy sort of pattern showing up. Not only do we identify that wavy pattern and it's much clearer to see, we can match that with potentially a sine wave or some other kind of wavy pattern. And we can also note approximately how much noise there is in that data. Again, all data has a certain amount of noise. It's not all perfectly going to fall on our trend line, but this gives us a way of visually identifying, is there a lot of noise or just a little bit of noise in our data? So all these things are very helpful when trying to analyze data. Graphing it is an extremely helpful tool. So before we jump into the specifics of, again, each individual program, Excel, Google Sheets, and LoggerPro, some general pointers. When you're making these graphs, it can be really easy to switch which variable is on which axis. And that's going to change how we interpret that data. It's going to change the best fit equation. So when you make this graph, I strongly recommend pick a couple of points from your data set and just kind of check that those data points are in the right spots on the graph to make sure that you have the correct values on the correct axes. We always want to make sure that in any physical measurement, we include units. But include those units in the axis titles. Don't include them in the values of the cells. Because in a lot of graphing programs, if you try to put oh, this is a distance in meters. So you put a numerical value with an M for meters. Well, in most programs, the computer is not going to know how to interpret those units. So just leave the units in the axis titles and just have the numerical values themselves in the individual cells. Sometimes the program won't even graph the data if it involves some of those letters. Okay. When you're displaying the data, and part of this is just kind of personal preference, things I think look a little bit neater, but these are pretty common conventions to use. Generally use unconnected points for the data, so just have dots for each data point, and then the best curve, that's going to show the overall trend line that fits the data as accurately as possible. Also, ideally, whenever you're looking at data, you want to look at as wide of a set of data as possible. If I have any small data set and a couple of points making that data set, if it's looking at a small enough section of data, pretty much any pattern is going to look linear on a small scale. You have to get a wider range of data to see, oh, is there some curve to that data? How is that curve changing? We want to look at as wide of a range of data as possible, but often this is going to be limited by the details of whatever experiment you're actually performing. So again, not always something that we can get. Once we have our data, we kind of have to work with the data that we have. Also, it's best to include a best fit equation, which kind of mathematical pattern best fits your data, along with the R-squared value. We'll talk about what that R-squared value is. Basically, very, very briefly and unspecifically, it's essentially a measure from 0 to 1 of how much of your data is explained by this best fit equation, with, again, 1 being your data is perfectly explained by that best fit equation. There's no other noise or other kind of trends involved. And as you get further away from that, it's less of a good match between your data. And in most cases, again, it depends on exactly what kind of data you're working with. If there's a lot of noise in that data, you're going to have lower R-squared values, but we want that R-squared value to be as close to 1 as possible. And that can actually help us identify which type of best fit equation is going to be best for us. And lastly, when you're looking at these graphs, you generally want to scale your data so that your data uses the entire space on the graph. Make sure you also label your axes, again, with units, because those units are going to be important on how we interpret that data. So again, just best practices, so when someone is looking at your graph and trying to interpret what your graph is saying, the data is as clear as possible. So we're going to be doing this with a couple of different graphing programs, again, Excel, Google Sheets, and LoggerPro, and we're going to be trying to make 3 different kinds of graphs with each one: a linear fit, a power fit, and an exponential fit. And we're going to be specifically looking at, first, how do we make these scatter plots in each of these programs? How do we generate the best fit equations and the best fit trend lines for each one? And kind of looking at any of the little idiosyncrasies that each program has and trying to, do some preemptive troubleshooting with this. So that's what we're going to be looking at next. So let's start with seeing how to make these scatter plots in Excel. I'm using the version for PC. Versions of Excel for different operating systems might have slightly different functionalities, might be a little bit different, but hopefully this is general enough to match with most versions. Now, when entering the data into Excel, I strongly recommend make your first column the variable that you want to have on the horizontal axis, and then make a later column the value that you want on your vertical axis. Excel, it can be a little bit difficult to change which axis is which, so starting this out at the beginning is very, very helpful. So on the horizontal axis, let's say I'm going to call this a variable x, and if this had particular units associated with it, this is where we'd want to enter in the units, on the axis titles, not in the actual values that we're going to be putting in later. Again, if you put meters or some kind of units in there, it might not recognize, and it might not just graph it at all, or think you have some description of something. It might mess up the graph. So again, any units, make sure you include units, but make sure you include them in the axis titles. So let's call that variable x, and this is going to be the quantity that we want on the vertical axis. Okay. So now let's say I'm going to use my data that I'm going to have a linear fit for, and let's just input the data. Okay, so now we've got our values that we're going to have on the horizontal axis, those variable x, and the values that we're going to have on the y-axis, the vertical axis, variable y. So to select the data to actually make this graph, you can click and either click and drag to highlight the two columns that you're going to want. Again, the first one being the variable that you have on the horizontal axis, the second being the variable that you have on the vertical axis. Or if they're more spread out, you can click on, again, that column title for one of them. So this would be column A, and I can click on there. And then you can hold Control and click your second column of data. Okay. But we just want column A and B, and we can go to Insert up here, and we want this scatter plot. So we've got this icon right here, a graph with a bunch of dots on it. And again, in most cases, we just want the graph with individual unconnected dots. And then we'll eventually use a trend line to show what is the mathematical pattern that best fits this data. Okay. So let's select that. Again, a very helpful check to do early on is to make sure that you have the correct values on the horizontal axis and on the vertical axis. So if we take a particular data point, say 0.6 on the horizontal axis and 5.2 on the vertical axis, we can look and see if that point is properly graphed. So on the horizontal axis, between 0 and 1, we've got 0.6, go up and around 5.2, excellent, we've got a data point there. If I look at a data point on the other side of the graph, we've got horizontal is 8.5 and vertical is 23.1. Excellent, we've got that data point. We haven't flipped the different axes. Again, in Excel, it can be kind of difficult to switch which values on which axis. So I recommend just planning early and saying, I'm going to put the variable that's on the horizontal axis in the first column and put the variable that's on the vertical axis in the second column. We might want to add some features to this graph. So if I click on the graph, we can either add chart elements over here with this little plus sign. And again, it gives us a number of different options. We can add axis titles, so those will show up, and then we can change this to, variable y, including the units. Do the same thing for the horizontal axis. Do the same thing for the chart title, change it however we want. And also notice that all of these chart elements can also be found by clicking on the graph, making sure you're on chart design, and then looking at this button over here, add chart elements. It's got the same set of options. Okay. So the one that we're going to want to specifically add is this trend line. Now, there's a lot of automatic options that show up on here. I recommend going to more trend line options. So I'll click on that, and let's also move this graph over so you can see the graph in its entirety. If you click off of that trend line, it's going to change what property we're looking at the options for. So if you click off of that, just click back on the trend line, and that'll show up again. Okay. So first off, we've got the choice of what kind of a trend line are we looking at? Is it an exponential, linear, logarithmic, polynomial of different orders, power fit? We get quite a few different options for this one. If we scroll down in this window, we get down to display equation on chart. So we usually want to select that. And we also have display the R squared value on the chart. Okay, so those will show up on the chart. You can kind of move them around however you want. And I'm also going to make this a little bit larger. So let's do that so we can see that equation and the R squared value a little bit more accurately. Okay. Now, again, this R squared value is a measure from 0 to 1 of how well our data is fit by this particular trend line. That's not an exact definition. There's a specific formal mathematical definitions, but that'll be good enough to go on with for now. So if I try different kinds of fits, notice for the linear fit, we get really close to 1, 0.998. If I try an exponential, well, it's still a pretty good fit, but my R squared value isn't quite as high. Logarithmic fits, power fits. Polynomials, you have to be a little bit careful with, because if you have few enough data points and a high enough order polynomial, then it can just automatically be fit to it. So sometimes polynomials might not be the best one to use, but it looks like our linear fit is, pretty much just as good of a fit as the polynomial was. Okay. We can also see that for this linear fit, we get the exact equation for what mathematical pattern best fits this data. So the equation for a straight line is y equals slope times x plus my y-intercept, and the computer will tell us what is that best fit slope and what is that best fit y-intercept. Okay. So again, this allows us to identify what is the pattern that is suggested that is the best fit to this particular set of data. Okay. Again, there are a bunch of other options that you can play around with in here, but these are the main things that I want to focus on for how to make these different kinds of graphs and add these different kinds of trend lines. So now let's change things up, and instead of looking at this linear fit, let's change over to the power fit. So we've got the same values for x. I can generate this graph in the exact same way, but let's change the y variables to go with this proposed power fit pattern. Notice that Excel is kind of nice in that it will automatically rescale the graph to give a pretty good use of the entire graph space for your data. So it automatically kind of rescales on its own. If you want to change how that thing rescales, if you double click on the graph and then click on these axes and then these axis options, this kind of bar graph icon over here, you can change what those bounds are. You can change where you have different tick marks on there. But again, Excel does a pretty good job at generating this automatically. Okay. But let's do a couple of things for this. Let's first make sure that the data is actually matching with what's on the horizontal axis and what's on the vertical axis. So again, if we look at this data point here, we've got 0.6 in the horizontal direction and a little over 2 on the y-axis. So, okay, that data point seems to match up. We're probably good to go with that. So let's say I double click on that graph again, and let's look at this trend line, because in this particular case, my linear trend line does not quite seem to be fitting the data as well as it did in the last case. And again, we can look at different kinds of trendline equations and see which one gives us the R squared value that is closest to 1. So linear, pretty good, but could be a little bit better. Logarithmic, about the same. Polynomial, again, polynomials can kind of look a little bit better by accident unless you're looking at a really, really wide range of data. But when we look at this power fit, yeah, that one seems to be doing the best. Okay. So we get this power fit, and again, for a power fit, the form of the best fit equation is going to be y equals some constant times x to the power of something, to some numerical power. Okay. And a lot of different kinds of physical systems show this kind of power fit. So these are very, very common equations to use. So sometimes our data is going to show this power fit pattern. Okay. Let's look at one more, the exponential fit. So again, I'm going to reset this data to look specifically at the exponential fit. Okay, so right now we're still using the equation for the power fit, and that doesn't seem to be matching our data super well. So let's again get those options up by double-clicking on that trend line. And in this case, well, linear fit, again, not great. Logarithmic fit, not bad. But if we go to the exponential fit, that one matches this particular pattern. So again, the general form of an exponential fit will be y equals some constant times e to the power of some other constant times x. Okay. And again, when we're looking at a particular set of data, if we get this exponential pattern, again, that tells us something about how these two variables in our experiment relate to each other. We can compare that with different claimed equations on how these two variables relate to each other. But in each of these cases, whether we have a linear fit, a power fit, or an exponential fit, the way that we generate these graphs in Excel is going to be pretty similar. So we enter the data, again, making sure that we don't include units on here, because if I put, let's say, switch that for 1 meter and hit enter there, notice that data point goes away. Okay, it doesn't know how to interpret that 1 meter value. So I think it might be just setting that to, something else, or not including that in our data. Again, when we enter that in, something goes wrong, and we want to correct that. Okay. So let's look at how this will work in Google Sheets. So let's have a look at how we're going to make these graphs in Google Sheets. Once again, we have to input our data, and I do still recommend putting in column titles with the units that are going to be used. So let's call this one variable X. Again, if it has units, this is where we want to put the units. We do not want to put the units in the actual numerical values, because again, that's going to throw off how the computer tries to graph this data. And let's call this one variable Y. And let's start with our linear fit. I'm just going to enter this data for the linear fit. Okay, so we've got our values that we want to graph on the horizontal axis. That's going to be variable X. And the graphs that we want to put on the vertical axis, that's going to be variable Y. So the way that we can make this graph is we can click and highlight both columns. Again, you can click and drag, or click one and then hold Control and click the other one. And then we're going to go to Insert, and we want to insert a chart. Now, with these kinds of charts, a lot of the time, Google Sheets is pretty good at trying to predict which kind of chart you're dealing with. But if you go up in the chart editor, and you can get to that chart editor, if that's closed, you can just double click on the graph. That'll bring up the chart editor again. And if we look at this, the setup part, if you go to setup, then it'll have chart type. We just want to make sure that we've got our scatter plot. So on this list of charts, this one was already suggested, but we want to make sure that is the scatter chart. We can make sure that we are looking at the correct data points, again, by checking an individual data point. So say, looking at a little after 2, so let's do the 2.3 and 9.5. So a little bit after 2 on the horizontal axis, a little bit underneath 10 on the vertical axis. Looks like we're graphing these data points correctly. Okay. Now, if we're not graphing these correctly, we can go to Setup, and then if you click this in this data range portion, for the x-axis, you can select which variable you're looking at. Again, it'll record those chart titles. Or if you want to highlight something on the graph, this is a little bit in the way. Let me move this out of the way before I select this. If I go on the graph, then I can select a specific data range, maybe from a different column, and say, okay, that's going to be on the x-axis. And the thing on the vertical axis, that's what we have for series. So again, I can select what I'm putting on the horizontal axis and what I'm putting on the vertical axis. A couple other features that we can look at for this. If you click on the axis labels, then you can set what sort of range you want. Again, Google Sheets is also pretty good at picking the full range of data, so your data will match with the size of the graph. But maybe I want this x variable starting at 0. So then, again, I click on that horizontal axis. I'm looking at customize the horizontal axis, and that minimum value, I want that to be 0. So it's rescaled that axis to allow this thing to start at 0, 0. If we now want to put a best fit equation onto this graph, we can go to customize, and then in this customize we've got series. So go to customize series. You can also adjust how this is being displayed, the color of the dots, the size of the dots. But we want to go down here, again, this is in customize, then series, go down to trend line. And when we select that, it will take a guess at what kind of trend line we want. Right now it's listing as a linear, but we can pick exponential, a polynomial, logarithmic, the power fit, it's called power series on here. But for this one, we just want our linear trend line. Again, there's a couple of options that we can adjust for this. And then we want to use the equation as our label. So where we have label on the same part where we've picked our trend line, we want to hit use equation. And up here, that will identify the specifics of our best fit equation. So this would be the equation y is equal to, again, for a linear fit, it is slope times x plus the y-intercept. So for this graph, our slope is 2.22 and our y-intercept is 4.15. We generally also want to include that r squared value. And notice that for this particular set of data, it matches up very, very nicely. So we get an r squared value very close to 1. If we were to try a different kind of graph, like let's say an exponential, doesn't fit quite as well. The r squared value isn't quite as close to 1. Same if we did a power series, again, doesn't match up quite as well. So in this one, we want the linear graph. And then again, once we have this best fit equation, this is the best fit, the best mathematical fit for this particular data that we've gathered. Let me close out of that. And if we have some claimed equation that we're comparing against, then we can look at that claimed equation and look at our best fit equation and try to match terms up with each other to figure out what does this slope and what does this y-intercept physically correspond with. So let's change that around. We've looked at the linear fit. Let's change this around and put in the numbers for a power fit instead. So all I've done is switch the y variables out for the y variables from the linear fit to the power fit equation. And now when we look at this graph that we've produced, again, we can check a couple individual data points, make sure everything is lining up correctly. We've got the right thing on the horizontal axis, the right quantity on the vertical axis. And now note that this linear fit doesn't match up quite as well. Well, we want to look back at that chart editor. So if you ever close out this chart editor, you can get back to it just by double clicking on the chart, really easy. And if we want to adjust this best fit equation, well, we go to customize, series, and then here's our options for the trend line. So the linear fit isn't terrible, but there seems to be something else going on here. So for this one, we want to use our power fit or power series. And when we plug that in, we get an r squared value very, very close to 1. This is a very, very accurate fit. And again, we get this fit equation for a power series, for a power fit. This is in the form y is equal to some constant times x to the power of some other value. And once again, if we're comparing this with a claimed equation, then we can compare our best fit equation from our data with the claimed equation, match up terms, and see if this is what we expect for the value of that coefficient in front of everything and the value of that exponent. Let's try this for the exponential fit as well. So we're just going to change these variables to the ones for our exponential fit. Okay, so once again, if we have the wrong kind of fit, our r squared value is going to get a little bit further from 1. Usually they're still pretty good. Again, it depends on how much noise your data has, of how close you're going to get to an r squared value of 1. But if we change can go into series, customize series, we can look at the trend line. If we put this to an exponential fit, notice we get a much, much better match. And again, once we have this fit equation, in this case it's an exponential, y is equal to a constant times e to the power of something times x. Well, if we take that equation that describes our data, the best fit for our data, and we have some claimed equation, we can line up those terms and see if these values that the computer is just spitting out at us have any physical interpretation. Can we compare that with some expected values for those? Okay. Again, there's lots of other features that we can look at for any of these graphing programs, but these are the basic ones for making these scatter plots and getting these best fit lines. So let's also have a look at Data Studio. So let's also have a look at how we can make graphs in LoggerPro. So let's have a look at how we can make these graphs in LoggerPro as well. Now, unfortunately, this isn't a free program, but a lot of my students use it. I use it for a number of different courses, and it does have some pretty nice functionality, but this is not a paid promotion in any way. So let's kind of go through this one real quick. When you open up a new window, it'll have a data table and a graph already set up. You can change the labels of this table by just double-clicking on them and saying, oh, I want this to be variable X, and again, you can give it a short name and give it some units. So when you hit done, that'll automatically update both the data column and the axis labels. And we've got what we're graphing on the horizontal axis, we've got what we're graphing on the vertical axis, and let's just start inputting the values for our linear fit. So a couple of things to notice is that the program will automatically graph the data as you're putting the data in. It automatically assumes that we're working with a scatter plot, and it will autofill that data. We can, again, check to make sure that we've got the right values on the right axis. So, around 0.6 on the horizontal direction, we look up, and then we've got a little over 5 on the vertical axis. So we're graphing these points correctly. If we had accidentally flipped our data columns, if you click on any of the axes, you can just automatically click on those labels and change what variable we're looking at. Okay. We do want Y on the vertical axis and X on the horizontal axis. You can change the scales of any of these graphs by just basically clicking and dragging. If you click on the middle of the axis and drag back and forth, it will slide that axis to the side. If you click and drag near either of the ends, it will hold one end fixed and rescale the graphs in that way. But most of the time, you're just going to want to hit this capital A button up here, and that will auto-scale the graph for you. We can also change the axis by clicking on either the bottom of the axis or the top of the axis and literally just enter in where do we want that graph to start. So let's kind of use this as our graph, and we also want to be able to put in a trend line. Okay. So this option right up here, this curve fit, if you click on that, it will give you a ridiculous number of options for different kind of fits to apply. The ones that are most often looked at are the linear fit, quadratic, there are other kinds of polynomials in there, power fit, and natural exponent fit. Those are the ones that we most often use. So if we click on linear fit, and then down here hit try fit, it will generate what is the best fit for that data, and then we can hit OK. We can click and drag that little label that shows what our slope is, what the y-intercept is, and also this program can actually say what the uncertainties in those are. Since our data points don't all exactly line up with that graph, it has a way of calculating what are the approximate uncertainties based on those data points that we're looking at. If that's not showing up, if you double click on this window itself, there's an option for showing uncertainty, changing how many decimals of precision that we have. There's a number of different options for that. Okay. So notice that our linear fit, again, matches up quite well. we've got a correlation, which is closely related to that r squared value. It's not exactly the same thing, but it's pretty close. We've got a correlation value in there, and we've got, again, both the slope and the intercept and their uncertainties, which is kind of interesting to work with. So let's change this up and say, what if we were looking at our power fit instead? So I'm going to change this data to the power fit one. So again, when I change those data points, this one doesn't automatically rescale the graph, but it does just have this button on here that we can just hit that auto scale button, maybe click on the axis down here and say we want it starting from 0. Again, we can adjust any of those different sides to kind of make the graph fit the region of that table as accurately as possible. And again, we go up here to the curve fit, click on that, and for this one, we want our power fit. Again, that has the form a constant times x to the power of some other constant value. We click power fit, hit try to fit, and hit OK. Now, it is worth noting that some of these programs use slightly different algorithms for generating these best fits, and as they're generating this best fit data, they'll kind of stop at different points. So sometimes these fit parameters that we get are going to be slightly different from each other. So that's just something to kind of note. But we still get, for this power fit, which has the equation y is equal to some constant times x to the power of some other constant, we can get those constants for a and b, and this should be pretty close to what we got for the when using the other programs. And as always, when we get these best fits from our data, these best fit equations, we can take that best fit from our data and compare it with some claimed equation. And we can try matching up terms, matching up the forms of those equations, matching up certain parameters in those equations to try to identify what does the coefficient in front physically correspond with, what would we expect if that claim was true, and same thing for the exponent. What exponent would we expect to get based on our claim? And this allows us to compare our data with our claim. Does our data support the claim or refute the claim? And let's look at one more example of this. Let's look at the exponential fit. So I'm going to change these numbers to our exponential data. Once again, we're going to have to usually just auto scale. It gives you a pretty good fit for that set of data. And once again, we hit curve fit. And for this one, we want the natural exponent. Okay. So we can hit try fit and then hit OK. Notice this exponent fit is slightly different than the exponential fits that we had for the other two programs, because this has an extra term in the equation saying, is this offset up or down at all? Is there a constant point being added to this? So the fit is a little bit different, so we do have to watch out for that, but we can still identify these different terms, and again, this program also gives us the uncertainties in those terms. So again, hopefully this is helpful for making different kinds of graphs, making these scatter plots, and applying these best fit equations in different kinds of programs. As always, if you have questions about any of this, or if there are important things that I've missed in here that I should update in a future video, please let me know. Otherwise, thank you for the review.